Welcome back to another round of differential equations. This time we're going back in linear ordinary differential equations, but we are adding a little spice to it. We're adding the Bernoulli case. So some textbooks, some teachers may call this the Bernoulli differential equation, but this is a linear differential equation that is a special case. That's why I'm saying it's Bernoulli case. So it looks pretty much like the ordinary differential equation, except with the inclusion of y to the r in here. R is any number that is not zero, essentially. So how do we get around solving this? Hmm. Wouldn't it be nice if this y to the power r doesn't exist right here? Let's try dividing both sides by y to the r. So this then becomes 1 over y to the r, or let's make it easier, y to the negative r, and then dy over dx, plus p of x, and then since we are multiplying this by y to the negative r, y times y to the negative r, this is y to the 1 times y to the negative r. We just have to add the uh, exponents here, so we get y to the 1 minus r. And then the right side is q of x. Now the q of x is alone, just like the linear ODE, but there's a lot of things happening in here right now. So how do we get around solving that? Well, what if y to the 1 minus r is v? Let's substitute y to the 1 minus r with v. So what happens here? Well, what's the derivative of this? So the derivative is 1 minus r, then y to the 1 minus r minus 1 is going to be negative r. And then derivative of y, dy over dx, this is just the chain rule. And then derivative of v, which is dv over dx. All right, so let's substitute everything in this. So this becomes y to the negative r dy over dx is this one. So this is this one that matches, but it still has this one. So we can divide both sides to get y to the negative r dy over dx equals 1 over 1 minus r dv over dx. So we can replace that with uh, this one becomes 1 over 1 minus r dv over dx plus p of x v equals q of x. Now, p of x and q of x, they can be any function you can think of, which is in x. So, if I multiply 1 minus r to both sides here, this will result in a different function that is also just also a function of x. So we can say, I don't know, let's just say this is p2 of x. So it's just another function, but this has a different name. Then similarly, let's denote this as Q2. Oops, sorry. What can we see here? This is the linear. This is another linear ODE. And from here, we can use the usual suspects. So the special integrating factor, which is this. So we can use that and whatnot in order to solve fully the differential equation. So let's use that on a question. Dy over dx plus 4 over xy equals x cubed y squared. X cubed y squared, this is a sign that this is a Bernoulli case, and the fact that this is linear tells us that this is indeed Bernoulli. So how do we get around this? Well, let's do what we did earlier. So y to the negative 2 times dy over dx times 4 over x. So plus 4 over x times y to the negative 1, in this case, equals x cubed. So y to the negative 1 equals u, let's say. This is the same as if we went here and said this y to the 1 minus r. 1 minus r is 1 minus 2, which is y to the negative 1. So that is a valid thing. You can start by doing that early on. so you don't have to do it later, but we can still do it here, so no problem. So derivative of y to the negative 1 is negative y to the negative 2. dy over dx equals du over dx. Since it's positive, we have to isolate this. So y to the negative 2 dy over dx equals negative du over dx. I used u here because I like the letter u, and v can be used as a, you can use that v, x, yeah. I don't know, not x because we're already using x and y here. So you can use any letter you want. I just like to use u. So that's why. Anyway, uh, this, see here, this matches this. So we can put negative du over dx plus 4 over x, and then y to the negative 1 is u, and then x cubed is just x cubed, so x cubed. From here, we can multiply both sides by negative 1 to get du over dx minus 4 over x times u equals x cubed, negative x cubed. So this is linear now, so we can use the special integrating factor, which is e to the power of integral of p of x dx, and we can solve for this. So p of x in this case is negative 4 over x. So e to the integral of negative 4 over x dx, this is equal to e to the negative 4 ln x. You can check that for yourself, but it's negative 4 ln x. Now, we can further simplify it by doing this. So I'm just putting negative 4 out. And e to the ln x, we know is x. Then to the negative 4. This is 1 over x to the 4. So we have to multiply that in order to get an easily solvable question. So let's do it. So 1 over x to the 4 du over dx minus 4 over x to the 5 u equals negative well, x squared, x cubed over x4 is 1 over x. And there we go. So now we know for sure, since we use the special integrating factor, that this is 1 over x to the 4 times y. No question about that. You can check that for yourself, but this is the case. And then we have negative 1 over x on the right hand side. We integrate both sides with respect to x. Take note that the derivative of the integral of a derivative, or the derivative of an integral, is itself. So we cancel the derivative and an integral out. So we get on the one side y over x to the 4. Oh, not y, u, sorry. Miswrote. U. This should be u. U over x to the 4 equals negative ln x. Yeah. ln x plus c. Well, let us isolate u. U becomes negative x to the 4 ln x plus c, but we're not done because we know this is from here y to the negative 1 equals u. So that means y to the negative 1 is this, and y to the negative 1 is 1 over y. So to finish this, y is equal to 1 over negative x to the 4 ln x, absolute value, plus c, we forgot x to the 4 here, sorry, plus c x to the 4. That is the general solution for that question. All right. So let me just recap. There you go. All right. Next question. dy over dx plus y cotangent of x equals y to the 4th cosine of x. There's y to the 4 here, so we can again let we multiply both sides by y to the negative 4 in order to get this. All right. Now that we have that, we can have y to the negative 3 equals Uh, what do I pick? Let's just pick v. I just feel like picking v for now. So, uh, the derivative of the left-hand side is negative 3y to the negative 4 dy over dx. On the right-hand side is dv over dx. All right, I agree on that. And so we can let's isolate y to the negative 4 first, since it matches with here. So y to the negative 4 dy over dx equals negative 1/3 dv over dx. So let's go here and replace everything. Substitute. So negative 1/3 dv over dx plus y to the negative 3 is v. So let's say v cotangent x, and then cosine of x is just cosine of x. That's it. Let's arrange this together so this can be clean. So we get dv over dx minus 3v cotangent x equals negative 3 cosine of x. Now, this is a linear differential equation. We can use the special integration factor, this one, again. So, what is the p of x here? It's negative 3, then cotangent of x. So now that we've identified the functions that we need to integrate, we can put it here. So e to the integral of negative 3 cotangent x dx. And if you need a reminder, this is negative 3, sorry, let me put it here, ln of sine x, which can be thought of as e to the ln sine x, and then to the power negative 3, which is, well, sine x to the power negative 3, or this could be cosecant cubed x. From here, let's multiply cosecant cubed x to the original. We get this. Cosecant cubed x dv over dx minus 3 cosecant cubed x cotangent x v times v equals negative 3. Well, here is cosine, and cosine's best friend is sine, so we can express cosecant as sine. So we can express that as cosine over sine cubed x. From here, we know that this is cosecant cubed x times v when the derivative of that with respect to x. This is because of the product rule again. On the right-hand side, we get negative 3 cosine x over sine cubed x. And now you'll see why I arranged the right-hand side that way. So we can integrate it more easily. Right, this and that will cancel out, so this will become v cosecant cubed x. On the right-hand side, we get negative 3, and then how do we solve this? Well, we know cosine x dx is derivative of sine x is cosine x dx. Oh, just derivative actually, not d over dx. Just d of sine x is cosine x dx. So whatever this is, we can think of it as the derivative, the d sine x. So it's like 1 over sine cubed x d sine x. This is basically a shortened version of integration by substitution, but I can tell you that the answer is, let me look at my notes, 3, uh, positive 3 over 2. Hold on. The answer is positive 3 over 2 cosecant squared x. Cosecant because it's sine x in the denominator, so it's cosecant plus c. Can't forget plus c. So let's just put sine in the, yeah, yeah. Let's just put it like that. Anyway, next we get we isolate v. Va then is equals to, we just have to multiply cosecant cube x here and divide by cosecant cube x, sorry. and we get 3 over 2. This becomes sine x. This becomes c sine cubed x. We remember that v is 1 over y cubed, so we have to do that. Now you can do one of two things here. One, you can isolate y, which will get you this 3 over 2 sine x plus c sine cubed x to the power negative 1/3. You can do that, and this is a function of y. Or you can also do this. You can multiply both sides by 2 and y cubed, the denominator here, so it's only single line, like this. 2 equals y cubed sine x plus cy cubed sine cubed x. If you're looking for a function, this is the way to go. But if you're looking for a clean equation, this is also a way to go. There are similar functions that have like similar graphs, and they fulfill the original differential equation very well. This is the general forms of the original differential equation that we have. There will be no particular solutions here, so that's going to be our final answer. So I will see you on the next video. Bye bye.